Yeah, where are we getting your homework back? So I can ask questions on my homework.
Well, the people who turned them in on the due date have them back. You know?
Yeah, but it's been a week later.
I don't know. I mean, I'll get it back as soon as I can. But that was my priority then, and now I have other priorities. So I'll get it back when I can. Anybody? No homework questions? No, just the final. I mean, we do have a final. Oh yeah. Hopefully this week I can get those back.
So can we expect not to see it before the final?
I don't know. I'm trying to get stuff done as quick as I can. Okay, so last time we talked about forced oscillations. And we dealt with a case like this. And then we had this forcing function f that's equal to f sub 0 times the sine of omega 0 t. And we came up with a final solution that had this form, x as a function of time is equal to a times the sine of the quantity square root of k over m times t plus phi. So that was the homogeneous solution. And then we had a second term that was, I think I had it in a different form than this, but it was like f sub 0 over m all over k over m minus omega 0 squared. So that's a coefficient times the sine of omega sub 0 t. And that was the particular solution. Sure. K. Okay. And this is the particular solution. And you can rearrange, you can rewrite the coefficient of that particular solution as f sub 0 over k all over the quantity 1 minus omega 0 squared over omega n squared. And if you rewrite it like this, it shows that there's a singularity when omega sub 0 is equal to omega sub n. If those two are equal, then omega 0 squared over omega n squared is 1. The denominator goes to 0, And so you have this particular solution, like explodes, goes towards infinity. So it doesn't tell us anything. That's a singularity. It doesn't tell us anything specifically when those two are the same. But so this form of the solution tell us what happens at omega 0 equals omega n. But what happens is you get a resonance. And so those two have the same frequency. The oscillations get bigger over time, and you have a situation that's unstable. So it becomes unstable, and the oscillations get bigger over time. Okay, so that's sort of the key thing is you want to make sure that you don't ever have systems that are vibrating with a resonance in an engineering application unless you're using it to damage something or whatever. I suppose that's possible, but not very common. Anybody have any questions about that? What does that do? Mm-hmm. With vibrations, and that's damped. Or omega naught is the frequency of the forcing function. Mm-hmm. Yeah. Okay, we'll do it. I'll do it. Wednesday. Okay, so the last thing we're going to talk about is damped vibrations. And so this system, I'm going to set it up the same way. So we have a spring and a mass. And this symbol stands for a force that depends on the velocity of motion. It's referred to as a dash pot. Was some kind of physical damper that you put in things a long time ago, and now it's sort of a catch-all that represents any kind of viscous damping. I don't think so. Just a little dash. I don't think so, but I can't be totally sure. But the force applied by the dash pot is in the opposite direction of motion with a magnitude force that's equal to some constant c times the speed of the motion, so that'll be x dot. That's the velocity of the mass. And it's called viscous damping because that's what viscosity does. The force is proportional to the velocity. So with a viscous fluid, if you imagine like sliding something through syrup, something with a high viscosity, if you move it really slowly, that force is almost like the syrup isn't even there. But if you move it fast, it applies a big force resisting that motion. And so that's what any kind of fluid, lubricant, or any kind of, anything with viscosity behaves that way. And so this is different than friction as you've seen in the past. In the past, you've dealt with dry friction, which only depends on the normal force, but this depends on the speed that the thing is moving.
How does that relate to certain materials that are actually have a high viscosity, but when combined, they actually have a low viscosity? Like wax and metal. If you have wax on wood,
I've never heard of that before, but I guess what you would do is so you just need to, it's not I think you would just use it as like an approximation where in your specific environment, you'd have some constant C that would come from experiments, I think it's just dependent on the viscosity, but I mean, it's a measure of the viscosity, I suppose. The viscosity, I don't, well, and then I believe that when you talk about measuring something's viscosity, you measure it as something like force divided by velocity. So sort of a circular thing, but that's the idea of viscosity is like the faster the force gets big as the velocity gets big, tells you how viscous something is. Right. That's right. Yes. So a certain material has a certain fluid has a certain coefficient C that's a measure of its viscosity, and that's right. You can look it up in a table. Well, well, constants don't always have to be unitless. I think the reason U is unitless is just that it relates one type of force to another type of force. This relates a velocity to a force, so it has to have units. But now that I think about it, like you wouldn't just look up that value of C because that would be dependent on the. But for a certain material, you could look up a viscosity of it, and then I suppose you could possibly, in some cases, do a calculation to calculate what the C value is. I think more likely you just set up an experiment, and measure the force as the velocity changes. Temperature, yeah. Right, it would be temperature dependent. I think there are. Any other questions about that? Okay, so let's draw a free body diagram. So over here we have the force Kx. And over here we have the force Cx dot. And now we have the weight. Let's think about that. now. So, so if you, so the way I have that arrow drawn, if you move this in positive x direction, it stretches the spring, so the string pulls that way. So in this case, that should be positive. But this one should be negative because if you have a positive velocity and it's going this way, the force counteracts it. So that needs to be negative. So the force is always in the opposite direction of the velocity. And so Newton's second law says, and let's just use the x components, negative kx minus cx dot is equal to the mass times the acceleration, which is x double dot. And so you can write this as x double dot plus k over m x plus c over m. Let me rearrange these. So x double dot plus c over m x dot plus k over m x is equal to 0. And so this is the governing differential equation for an unforced, damped spring mass system. So I'll talk about that, but I'm not going to give you any problems like that. But the last thing I'll do is just sort of put all this together. I think it's sort of a simple picture in a way, but the thing to remember is that the cases that we're looking at specifically are just the ones that have simple closed form solutions. Okay, so what we're going to do is we're just going to guess that there's a solution of the form x is equal to some constant e to the lambda t, where this lambda is a constant. And once you choose something to try, seeing whether it works is pretty easy. You're finding the constants that it works for is pretty easy. So, x dot then would just be equal to lambda e to the lambda t. And x double dot would just be equal to lambda squared e to the lambda t. Yeah, these are all functions of t. And now we're going to, plug it into the governing equation. The governing ordinary differential equation. So we have lambda squared e to the lambda t plus lambda c over m e to the lambda t plus k over m e to the lambda t is equal to 0. And we can cross out, so divide everything by e to the lambda t, get rid of these. And you get this equation that says lambda squared plus c over m lambda plus k over m is equal to 0. Just solve that for lambda. Using the quadratic formula. And let's see, you get, so negative c over m. Plus or minus square root of c squared over m squared minus 4 times 1 times k over m. And this is all in a square root, all over 2. So those are our two roots for lambda. And I'll call those lambda 1 and lambda 2. And so then our general solution for this undamped system okay. So this is general solution for the, no, not undamped. This is for the damped system, unforced. Is x as a function of time is equal to some constant a times e to the lambda 1t, you know, where lambda 1 is one of those two roots, plus b times e to the lambda 2t. Where lambda 1 and lambda 2 are the roots from the quadratic formula.
Or is it girl my code for class who asked what the quadratic formula is?
Yeah, that happens. Yeah, I had a guy in one of my math classes who was getting a master's in math education and had never heard, he was going to be like a math teacher and he'd never heard of the quadratic formula.
Like, how does somebody get that high up in their career?
I guess you just happen, I mean, everyone's distracted time to time. I guess you're just, I don't know. I mean, it's hard to make excuses for that. But
like, you literally have somebody
yeah.
all college
yeah.
in order to say that. And Calc 1 and Calc 2.
Does it really come up with that much in college algebra, Calc 1 and Calc 2? I remember mostly from
yeah.
But it came up all the time.
It comes up all the time in physics 1. Like in projectile motion, you have to do it all the time, you know, because you have the things of parabola and you have the two, but yeah.
Physics
was easy, yeah. I've heard it's easy. Oh, I shouldn't talk about that on here. Okay, so we get is so this is the solution. But it turns out that something important happens when, anyone remember what the term is for the stuff inside the radical? Discriminant. So something important happens when the discriminant is equal to 0.
I went to the DMV this morning and got discriminated. So,
Do you? That sucks. So that's when c squared over m squared is equal to 4k over m. And so notice that's a relationship between the coefficient of damping, let's say the amount of damping, and the other two system parameters, K and M. So like you could say when C is equal to 4K M square root, pretty simple, 2 times the square root of Km. So at that point, that's what solves this. And that is where the system returns to equilibrium in the minimum time. And I mean, I guess it's not that it returns it to equilibrium, it's that it returns it there, you know, permanently, or basically gets it back, gets that vibration damped down faster than any other way. And so if you're designing a system, like if you're coming up with some kind of damper that's designed to eliminate vibrations, you want to find this this value of C. And this is called the critical, this is called critical damping. Yeah. Tell them how it is, C-crit. Thanks, B-crit. Okay, so here's what it looks like. You know, there are 3 cases. I mean, you could have so the first one is if your C value is bigger than C critical. It's called an overdamp system. And you get rid of the damping, you get rid of the vibrations fast, but it takes a long time to return to equilibrium. So an overdamped system, if this is the equilibrium, I'll draw the, okay, so here's an undamped system for reference. Here's the equilibrium location. An undamped system just keeps oscillating with a sinusoidal pattern. An overdamped system does this, but the damping is large, and so you can see it stopped. The oscillation disappears fast, but it's going to take a long time for that to return back to its equilibrium position.
Does it ever cross it?
In critically damped and underdamped systems, it does. In overdamped, it doesn't. I don't think ever. So the vibration disappears fast. But it takes a long time to return to equilibrium. Second case is underdamped. This is for C that's less than the critical C value. Yeah. And so in this case, the oscillations are getting smaller each time. But it takes a long time for it to die down. So with a decreasing magnitude, decreasing amplitude. Then the ideal case for most applications is the one where you get back to equilibrium the fastest. This is for critical. So this is called critically damped. And this goes something like, it does cross over, but then gets back down close to equilibrium fast. And mathematically, I think what that means is for any, you can choose any like epsilon value, like what you want to call staying, you know, you could say, well, what does it mean to have returned to its equilibrium position? Maybe it stays within 0.05 meters or 0.002 meters or something. You just choose some parameter, and then this is the fastest one, so that for all future times it's within that amount. So if you're just designing a damping system, this is usually the criterion you want to use for choosing the strength of your damper. Okay, let me say one more thing. Oh, any questions about that?
That's your one nice thing.
No, that was a question. Well, I guess they just measure the velocity and then exert a force somehow, but I don't know. I've never come across that. Electronic motor mounts. I don't know what that is. Mm-hmm. Oh, okay. Uh-huh. Mm-hmm. Yeah. Oh, huh. Cool. Uh, so what about um, problems with all this stuff? The deluxe model. Um, well, I think the key thing to understand about this is it's not too hard to come up with a governing differential equation. So finding the governing ordinary differential equation isn't any harder than these cases. It's just harder to find a closed form solution. That doesn't mean it's hard to solve numerically. MATLAB or Wolfram Alpha, if you come up with a differential equation and boundary conditions, they'll give you numerical or sometimes symbolic solutions to these. So let me just give like an example of one that has everything. And so let's say we have a force this way that's equal to f sub 1 times sine of omega 1t. And then we have another one here that's f sub 2 times cosine of omega 2t. And then over here we have kx and cx dot. Then the x component of Newton's second law says negative kx plus cx dot that should be negative. So negative kx minus cx dot plus f1 sine omega 1t plus f2 cosine of omega 2t is equal to mass times x double dot. And so x double dot plus c over m x dot plus k over m x is equal to negative f1 sine omega 1t minus f2 cosine of omega 2t. And that's a lot more complicated system, but it wasn't really any harder to come up with this governing ordinary differential equation. The issue is just nothing you learn in differential equations tells you how to solve that problem. Yes. Still not easily solvable. What if that just changed everything? Oh shoot, we have to start again at day one. But anyways, the thing to keep in mind is it's still easy to solve numerically, just not by hand. And you know, as you get, I don't know, probably all through undergraduate, the differential equations I'll deal with will be ones you can solve by hand because you can graph it out easily and stuff. But I think in many, if not most, if not virtually all applications, when you're working, doing research, or working in a company or whatever, once you get a differential equation, you're just going to solve it numerically. So these things that were like too complicated for us to deal with by hand, like in the way that you'll end up thinking about differential equations later, really isn't any harder at all. It's just I can't tell you in one line what the solution is. Yep. You're right. It also changes everything. Okay. Yeah, now, right.
So Wednesday we're doing trivia?
Yeah, so Wednesday we're going full seminar mode. But you can think of it as trivia, but we're not doing a trivia game. That much I promise you. But if you have homework questions or anything, bring them. I don't even know what that is. Oh.